So it's my pleasure to introduce Bruce Kleiner, that is going to talk about rough geometry.
Right, actually I'm talking about Gromov hyperbolic spaces and quasi-conformal analysis, which I guess falls in the general setting of rough geometry. So I'm going to continue where I left off last time. And I backed up a little bit here. So toward the end of the lecture, I was talking about hyperbolic spaces, or Gromov hyperbolic spaces. So these are a generalization of manifolds with negative curvature. Can you hear me? Yes? No? Try raising it. Is that better? Okay. Right, so space is Gromov hyperbolic if geodesic triangles are delta thin, meaning if you take a point on one of the three sides of the geodesic triangle, there's a point on one of the other two sides at distance at most delta. So went through some examples here, hyperbolic space, convex sets, trees, and then I recalled the Morse Lemma, which says that if you have a quasi-geodesic in a delta hyperbolic space, then and you take a geodesic with the same endpoints, the two sets are within Hausdorff distance d of one another, where d just depends on the constants. And this gives you quasi-isometry invariance of hyperbolicity. Then we have this statement about approximation by trees, given a finite subset in a Gromov hyperbolic space. Metrically, it's the same as a finite set sitting in a tree to within additive error. Okay, so.
There may not be geodesics.
I'm sorry?
There may not be geodesics.
I'm assuming that these are geodesic metric spaces. You can work in slightly greater generality, but I don't want to bother with that. Okay, so now I want to talk about the boundary. So, of course, in the case of classical hyperbolic space with the Poincare ball model, the sphere at infinity played a central role. So we want to substitute for that in the setting of hyperbolic spaces. So, okay, so to define this, I'll need a few definitions here. First of all, if you're given, so let's specify a base point, which I'll call star. So given 2 points in the space X, then the overlap of those 2 points with respect to the base point star is given by this slightly weird-looking formula. But if you think about the statement about approximation by trees, it has a very simple meaning. In a tree, if you have a base point and 2 other points, X and Y, then the union of the 3 geodesics is a tripod. Okay? And so you have, to get from the base point to X and Y, you travel along a common initial segment, which might have length 0, and then you branch off. Okay? So this initial length here is the overlap distance for these two paths. And you just work it out in the tree. It's exactly given by this formula. Okay? So this is the overlap. And that, in the tree, you can see is the same as the distance from the base point star to the geodesic from X to Y. And it's the same thing. Same thing is true here up to error comparable to delta. All right. So I'll come back to that in a second. Now, to define the boundary, we start by looking at geodesic rays. And so let's parameterize them at unit speed. They'll say they're asymptotic if when you look at the distance, as you move out these rays, you look at the distance at time t. You look at the points at time t and the rays, that the distance is uniformly bounded. And it's easy to see that's the same thing as saying that the images of the rays are subsets with finite Hausdorff distance from one another. Okay, so this defines an equivalence relation. And the set of equivalence classes is the boundary. Okay. Now, we'd like to promote that. Right now, it's just a set. We'd like to promote that to a slightly better structure. To do that, let me just make a remark that if you look at the look at a fixed base point star, and you take an arbitrary ray starting somewhere else, it's easy to see there will be a ray leaving the base point, which is asymptotic to your given ray. Okay? It may or may not be unique, but there exists such a ray. Okay? So in particular, every equivalence class or every asymptote class contains a representative leaving the prescribed base point star. All right? So now we can extend this definition of overlap to rays. So if you have two rays leaving the base point, the overlap is given by essentially the same formula, except you take the limit as points run out to infinity along the corresponding rays. And this overlap could be infinite. It'll be infinite if and only if the rays are asymptotic. Okay? And that's so to compare that with the finite situation from a minute ago, if x is proper, you take these two rays, the gamma 1 and gamma 2, well, then you can see there's going to be a geodesic, which is asymptotic to gamma 1 in one direction and asymptotic to gamma 2 in the other direction. And then the distance, that's this geodesic eta here, and then this overlap for the rays will agree with the distance from the base point to this doubly infinite geodesic, okay, up to additive error.
Additive error?
Up to additive error. So following Jeff, I'll say I believe this 4 is correct. But we're not going to check it. So now you can use this quantity, right? Given a pair of rays, now we're thinking them as points at infinity, psychologically, as the shift. The rays or equivalence classes are these points at infinity. Given two such points, if they're distinct, there will be a geodesic joining them. And then you look at the distance from the base point to that geodesic. Okay? And using that quantity, you can define a metric. So say a visual metric is a distance function on the boundary here, so on the set of these equivalence classes. So that if you take two rays leaving the base point, that distance is comparable to this quantity. You take the overlap, okay, to multiply it by some fixed number a, which is called the visual parameter. Take e to the minus that, and then that's the distance to within a factor. Okay? So, so in fact, you can show that if this a is sufficiently small, like somewhat smaller than 1 over delta, then the visual metrics always exist. You can start by just looking at this quantity here for a given a, and then you can argue that there will be a distance function which is comparable to that. Okay? So you have these visual metrics. Now, what do they look like? Let's start with Hn. So here, it's an exercise to see that if you take, say, the Poincare ball model, here's the origin. So you take 2 points at infinity. You look at the rays here. So the minimal distance, r, you take e to the minus r, that will give you the angle of separation between the initial velocities of these geodesics, or equivalently the angle between these 2 points in the unit sphere. Okay, it will give that to within multiplicative error. Okay, so this visual metric will be literally the angular metric on the sphere in the hyperbolic case. But that's not quite true, because notice when we talk about the visual metric, we have that parameter, that a. Okay, so if you take a to be equal to 1, then what I said is true. But if you take a to be less than 1, what you get is another kind of distance function, which you get from the standard angular metric by raising it to a power less than 1. Okay? So the metric is not unique. You have a whole family of metrics, okay, which depend on this visual parameter. Right? Now, so another case is
Take the maximal A?
I'm sorry?
Take the maximal A?
I think in general, it's you don't get a good metric when you do that. In general, certainly in many cases you do. Now, in complex hyperbolic space, so I mentioned last time that if you take, that has its own ball model. So if you take, so corresponding to the unit ball in Cn, if you take the origin, so then given a point on the unit sphere, you can look at the complex plane, a complex one-dimensional space, spanned by that. So it will be spanned by this direction and I times that direction, right? Now, those planes correspond to subspaces of complex hyperbolic space with curvature -4. And so actually what I wanted to do was to take something which is orthogonal to this plane. So I take some direction which is orthogonal and look at the plane spanned by this direction here and something orthogonal to this complex line. Okay? So that plane now spans a hyperbolic, with respect to the metric on complex hyperbolic space, that corresponds to a hyperbolic plane with curvature -1. Okay? And that gives rise to a circle at infinity, just like the hyperbolic plane is a circle at infinity. And so you see a curve, a standard circle with respect to the visual metric. Okay? And so more generally, to understand the visual metric in this case, what you do is you look, so this is the unit sphere, S2n minus 1. You look at each point on the sphere, you have the codimension 1 subspace of the tangent space, which is the orthogonal complement of the I times the radial direction. So this is the usual contact structure on the sphere. And then to get the visual metric to within a factor, you look at, given 2 points on the sphere, say P and Q, you look at paths from P to Q, which are everywhere tangent to this hyperplane field, the contact structure, and take the infemal path length. So that gives you the visual metric. So this is an example of a sub-Romanian metric or chronometric. And so if n equals 2, so you're looking at the complex hyperbolic plane, this is a metric on the 3-sphere, which has Hausdorff dimension 4. Okay? All right, so example of trees. So it's easy to work out. If you take, for instance, a tree, let's say, 4-valent tree, it's easy to convince yourself, if you make all edge lengths equal to 1, that the boundary in this case is a Cantor set. Okay?
So you want to move on these complex directions because the A is bigger there?
You want to avoid the complex directions because those have stronger negative curvature. You want to go in the totally real directions. So the distribution on the sphere, so in the sphere, choose a point on the sphere that corresponds to a vector, right, which you can think of as kind of the outward normal to the sphere. I times that will be a tangent vector. And then you're taking perp of that in the tangent space. So that's the usual context structure on the sphere, and you want to travel tangent to that. Okay. So another example I want to mention, probably shouldn't do this, but I guess I will. It's kind of a nice example to contemplate. So you can find examples. There are different ways of doing this, but you can obtain manifolds, let's say 3 manifolds with boundary, which are hyperbolic in the sense the curvature is -1, and the boundary is totally geodesic. So it's locally isometric to a half space in hyperbolic space. So with these objects, it's not hard to see that the universal cover embeds isometrically. It embeds isometrically in hyperbolic 3 space. And the image of this embedding is going to be a convex subset of hyperbolic 3 space. So if we work in the ball model, the convex set will have boundary, which consists of a disjoint union of hyperbolic planes. So in the ball model, those hyperbolic planes look like pieces of spheres which meet the unit sphere orthogonally. So we'll get some sort of picture like this. They're disjoint, so we get this pattern of planes. And the boundary in this case can be identified with the limit set of this convex set. So it's kind of the closure of this intersect the unit sphere. And you can check that closure has a very simple description. in terms of the planes. So you simply take, for each plane, which is a boundary component of this convex set, you look at the circle at infinity that it defines. So that, and then you look at the open spherical cap, which is kind of lies on the other side from the convex set, and you remove that from the sphere at infinity. So you remove a countable infinite collection of these open disks, and you're left with some set with empty interior. Okay, so the resulting compact set is homeomorphic to the Sierpinski carpet, but it has a rather different geometry from the usual Sierpinski carpet that one sees in the plane that you get from taking the square and removing this and then subdividing and so on. Okay. So another example, I guess I'll just pass over this. They're objects called Fuchsian buildings or two-dimensional hyperbolic buildings. They're two complexes with where any 2 points lie in a subcomplex isomorphic to the hyperbolic plane. Okay, I think I'll skip over that. Now, general properties of visual metrics. So if you don't impose any other conditions on your Gromov hyperbolic space, you can't say much of anything about the visual metric. Essentially, anything can arise. But let's suppose we're looking at a Gromov hyperbolic space which has symmetry. So for instance, we'll assume that you have a group G acting on X, where the action is discrete, co-compact, and isometric. Okay? Then you can say a lot about the structure of the boundary. So first of all, well, in this case, the boundary is compact. That just comes from the properness. But in fact, the symmetry of the space X is inherited by the boundary in the form of what I call approximate self-similarity. Okay? So the statement is the following. Well, maybe I'll draw a picture first. So it says that if you take so here's X, then we have the boundary. Well, maybe I'll kind of conflate the boundary with X. So if we take a point in the boundary and we take a ball centered at that point in the boundary, okay? So then that ball, so think of the radius as some number r, it could be extremely small. Now you take the metric on that ball and you rescale it. You multiply the distances by 1 over r. Okay? So you expect such an object to have roughly unit diameter. And the assertion is that the rescaled object is L by Lipschitz homeomorphic to some open set, say U, in the boundary. Okay? So everywhere you look at any scale, the boundary looks the same as the space of the top scale. Okay? So there's the precise statement. So this actually is quite easy to prove, starting from the definition of the visual boundary. But I think I'll skip going through that. But it does have a number of ramifications for the structure of the boundary. So one of them is that the measure is very nicely behaved. So the measure has a property called Alfor's regularity. So it's Q regular, Alfor's Q regular for some Q, and this means that if you take any ball, you look at the Q-dimensional Hausdorff measure of that ball, well, then it's comparable to r to the Q, okay, provided the radius is sensible. Okay? So there are different ways of proving this. One of them uses Patterson-Sullivan measure, and the way that the group distorts that. Okay. So another property is, so this doesn't hold in general, but if you assume that the boundary is connected, then it satisfies a very a quantitative version of connectivity, which is linear connectedness, which just says that given any 2 points in the boundary, you can join them by an arc whose diameter is at most a constant times the distance between the 2 points. Note what I'm not saying. I'm not saying that there's a path joining them whose length is bounded by a constant times the distance. Okay? So for instance, if you take hyperbolic space and you rescale it, okay, to make it sort of more negatively curved, then the visual metric may have no rectifiable paths at all. No non-constant rectifiable paths. Okay? So this isn't an assertion about the length. If you assume something much stronger, so if the boundary happens to be a manifold, so then, in fact, the manifold must be a sphere. This sort of comes easily from the dynamics. But the manifold property, the contractibility property of the manifold is amplified by the self-similarity, and it gives you a quantitative form of contractibility or local contractibility. It's linearly, it's called linearly contractible. So that's the following. So you take a point in the boundary, P. You look at a ball of radius r, okay? And then what it says is you can shrink the radius by a controlled factor so that the inclusion of the smaller ball in the original ball is null homotopic, okay? So this would rule out, for example, a picture where you have a metric on a sphere, but you have like on a sequence of smaller and smaller scales, you have sort of long, thin fingers, okay, where the ratio, the tip, the length to the girth goes to infinity. Okay, so yeah.
You didn't say anything about the metrics for the last three.
Yeah,
just describe the spaces.
Yeah, I mean, one can say a great deal. For reasons of time, I'm just trying to convey a flavor of what these objects can look like. Yeah. Okay, so now there was this other feature which showed up in the proof of Mostow rigidity, where you have a quasi-isometry, and this extends to the boundary, right? If you have a quasi-isometry of hyperbolic space, you get an induced homeomorphism of the sphere at infinity. Okay, so in the hyperbolic case, this generalizes as follows: if you have a quasi-isometry between two hyperbolic spaces, then there's an induced homeomorphism between the boundary. And in fact, this is what's called Quasimobius. Okay, so what is it? What is this Quasimobius condition? So it's a little bit unpalatable at first exposure, but it turns out to be actually a very clean way of handling a number of issues. So what does it mean to be Quasimobius? So definition: if you're given a metric space and a four-tuple of distinct points, just use this formula, so this combination of distances, which is sort of mimics the classical cross ratio, except you're using distances instead of the formula with complex arithmetic. And then say a homeo is Quasimobius if, there's a homeomorphism eta. Ignore that for a moment. The assertion is that whenever you take four distinct points in the domain, okay, then you apply the map F to that four tuple. Okay, you get a four tuple of points in the target, and then you calculate the metric cross ratio in the target. Well, then that is controlled by the metric cross ratio of the four tuple in the domain. Okay, so it's controlled in the sense that it's less than some function eta of the cross ratio in the domain. So this eta here is usually called the distortion function, governing how badly the cross ratio can be distorted.
Is it enough to know if you have nicely positioned points whose cross ratio is on the order of 1, their image is on the order of 1?
In reasonable spaces, yes. In complete generality, this is not. I think that's not true, but in reasonable spaces, for example, if you look at boundaries of the boundaries of the sort that we were considering, statements of this sort are true. You just need to check it for four tuples where the cross ratio is controlled.
homeomorphisms on some previous stages when f is equal to 1?
It's kind of the wrong question to ask. I mean, so it's. Let me come back to this in a minute. I mean, so in particular, that begs the question: what's the relation between this and quasi-conformal and the best constant and so on?
The role of normalizing everything happens after Newton's.
Right. I think this. I don't think there are clean or useful results in exactly that spirit, because this notion cleans up certain issues, but it doesn't fit well with that line. I mean, I'll come back to that later on. So there are other structures that you can use for stating things like this. Okay, so so here's the statement. Here was the definition of Quasimodia. So I want to explain why this is true. Why should this homeomorphism distort the cross ratios in a controlled way? So let's start with a quasi-isometry. So first of all, why is there any bijection at all between the boundaries? So remember, the boundary X is just the set of equivalence classes or asymptote classes of geodesic rays, right? So you simply take your well, but the map comes from the Morse Lemma. I mean, you have so you have X and Y. If you have an asymptote class over here, a boundary point is an equivalence class of geodesic rays. So if you take a geodesic ray here, you compose that with the quasi-isometry, what you get is a quasi-geodesic ray. So here's F composed with gamma, right? And now you use the Morse Lemma, which says that every quasi-geodesic ray is at controlled Hausdorff distance from some geodesic ray, okay? And so this geodesic ray over here will be the image of the corresponding boundary point here, okay? So that's where the bijection comes from. This bijection has the property that it respects the distance between geodesics. Well, what do I mean by that? So let's take 4 points at infinity. So 1, 2, 3, and 4, right? So if you take the first two, so there will be a geodesic in X, which in this direction gives you a ray in this asymptote class. In this direction gives you a ray in that asymptote class, and similarly here, right? And then you can look at the minimal distance between these two geodesics. Now you apply the quasi-isometry F to this, and you get a configuration which is a quasi version of that. Right? Now you apply the Morse Lemma to this configuration, geodesic, geodesic, and the segment. Okay? So the point is that this, you check that the length of this segment and the length of this segment will basically can be bounded in terms of one another by linear functions, just like the functions in the definition of a quasi-isometry. Okay? So that's the sense in which the distance between geodesics is respected by the quasi-isometry. Note the geodesics are specified by a pair of points at infinity and another pair of points at infinity. Okay? So it's really, that distance here is a function of pair at infinity. Okay? So then, so step 3 is to do a little bit of gobbledygook. So you just observe. So now let's think about this statement about approximation by trees. So you're given this configuration here up to additive error. That's just this kind of standard picture in a tree, right? This kind of Feynman diagram of where you have these two geodesics and this edge length. Now let's bring back our base point star. Okay, so well, when we join that to this configuration, well, maybe the shortest geodesic lands right there. Okay, again, I'm working in the tree approximation. And if you just unwind this, you look at this quantity here, which is this alternating sum of, these are the overlaps. Okay? These are the overlaps. And you work it out, you just find that this quantity here is this distance. Okay? Well, I'm lying a little bit. It might be minus that distance, or it might be 0. It depends a little bit, depends upon what ordering you take on these points. Okay? But in any case, you get that this quantity is, this kind of gadget here will be quasi-preserved by the boundary homeomorphism. And then finally, you just exponentiate this to recover the distance at infinity. This additive, if you exponentiate this, this thing here, what you get is essentially the distance between the corresponding points at infinity, if you recall the formula for a visual metric. Okay? So that tells you that the multiplicative, or the metric cross ratio at infinity will be quasi-preserved by the homeomorphism. Okay. So
that means this function's constant.
Which?
This quasi-preserved means it's just changed in ratio by a bounded amount?
It's changed. So in the additive thing, it will be changed up to the same sort of estimate you have of the quasi-isometry, upper and lower bounds by linear functions or affine functions. Okay, but then you have to exponentiate that. So, that translates into.
You get a specific. The function in the definition is some specific thing you can calculate.
You can, but it's you can write down some a priori control on asymptotic behavior, but I've yet to see a situation where that's really useful. But I mean, you're absolutely right. You can do this. So let me just mention other properties of these weird class of mappings, these Quasimobius homeomorphisms. So first of all, if you have a quasi-isometry, then it gives you a boundary homeomorphism. And the point is that if you specify the quasi-isometry constants, then you can determine the distortion function eta. This is this homeomorphism, which governs the relation between cross ratio and domain and target. So it's uniform. This eta is uniform depending only on L and A. In particular, if you look at an isometric action, then the induced action on the boundary is by uniformly Quasimobius homeomorphisms. Okay? So if you take two Gromov hyperbolic spaces with co-compact actions, then every eta Quasimobius homeomorphism between the boundaries arises from a quasi-isometry in this way, with control this is backward. This should be L and A, or functions of eta. That's not correct. Okay. Now, so another property of these Quasimobius homeomorphisms is compactness. This is similar to what we saw mentioned last time in regards to quasi-conformal homeos. So if you have compact metric spaces and you have a sequence of Quasimobius homeomorphisms with a fixed distortion function eta, then after passing to a subsequence, it either converges uniformly to a Quasimobius homeomorphism, well, with the same eta, or it converges to a constant map on the complement of a point. Okay? So relation with quasi-conformal, if something is Quasimobius, then it's actually quasi-conformal, where the constant, the QC constant just depends on the distortion function. Here you can take something like eta of 1, roughly speaking. So in particular, this is a stronger, being Quasimobius is in general a stronger property than quasi-conformal.
What spaces are we in now?
These are just say compact metric spaces. Okay. And if you're familiar with the notion of quasi-symmetric homeomorphism, well then well, there's more than one relationship here, but the simple one is if you take something which is eta Quasimobius, well then locally near each point it will be quasi-symmetric. Okay, where the
quasi-symmetric.
The quasi-conformal is where you sort of you look at the balls in the domain and eccentricity of their images, take lim sup as the radius goes to 0. The quasi-symmetry is more of a uniform condition. Okay? It's sort of where you...
Well, 1 is only for small.
Yeah, the quasi-conformal is for sort of infinitesimal balls.
Lim suit.
Yeah.
Okay. Oh, okay. Right.
Okay. All right, so now I want to shift gears and talk about sort of the more analytic, sort of the analytic side of the story. And to do that, I want to begin by talking about modulus, which, well, I haven't mentioned it yet, is kind of a key kind of ingredient in the classical story for quasi-conformal homeomorphisms. So let's take a metric space with some measure, mu. So then let's take a family of paths, so just some collection of paths, gamma, and a Borel measurable function, rho, possibly taking infinite values. So then you can define the rho length of a path by just a line integral of this function rho. Okay, so here I'm integrating ds. This means it's integrating with respect to arc length. All right, so in particular, this will be infinite if take this to be infinite if the path is not rectifiable. Okay. So this is analogous to using in Romanian geometry. You take the length of a path with respect to a conformal metric, where you think of rho as the conformal factor. All right. So the mass or the q mass for some number q is just the integral of the qth power with respect to the measure mu. And I'll say that this function, this Borel measurable function rho, is gamma admissible, where gamma is my fixed family of curves, if every curve in the family, every rectifiable curve, has rho length at least 1. Okay? And then the modulus, q modulus of gamma, is then femal mass of gamma admissible functions. So I take inf of mass, q mass of rho, where the rho is gamma admissible. So this is pretty weird if you haven't seen it before. But OK, so I can also talk about the q modulus for a pair of subsets. Takes two sets E and F. Then there's a naturally associated path family, namely the family of paths, which start at E and end at F, or paths which join E to F. OK. So just to give some idea of this, if you haven't encountered it before, let's look at the case where you have Romanian manifolds, and the measures are Romanian measures. So here, if you take some path family in the domain, now this is a little confusing. Now you take a map, a diffeo from Z to Z prime, and then you look at the corresponding path family in Z prime. Okay. So then, if this diffeomorphism F is conformal, then the modulus of gamma prime will be the same as the modulus of gamma. Okay? The point is that if you just run through the definitions, the conformal map will scale the volume element and the length element in exactly the same way up to raising to the power n. Okay? And so if you just apply the change of variables you see that you can transfer a gamma admissible function to a gamma prime admissible function by just putting in the right power of the Jacobian. Okay.
Back to the slide where you had the quantification over rho and mu, so the definition.
For modulus?
What about the measure? You know, do something
so I'm defining, the measure shows up here when I calculate the mass. I'm integrating
over the whole space or the family?
I'm integrating that over the whole space. Here, well, the condition of admissibility is a length, this condition on length, which brings us back to this. Right here, we're taking we're integrating the curve rho over each curve in the family. Okay. So the point is, this is conformally invariant, and if you take something which is k quasi-conformal. I'm taking these to be the Romanian measures. I'm taking them to be the Romanian measures. Okay. But
depends on you.
yeah. So it's really a notion for a metric measure space, a metric space together with a choice of measure. On the other hand, if it's quasi-conformal, then the modulus needn't be preserved, but it's preserved to within a factor. Okay, so it's quasi-preserved. So you have a bound like this. All right, so that's the idea. The modulus is a conformal invariant and a quasi-conformal quasi-invariant. And it links, the point is going to be that it links sort of the infinitesimal or small infinitesimal behavior of a mapping with kind of the bulk or macroscopic behavior of the map. So you can see this in by looking at bounds on certain modulus of certain families.
Greater than or equal to 2 there in this theorem.
Yes. Yeah. Thank you. Yeah, I should have said that.
So using the fact you have a Rod-Nikodym derivative for the quasi-conformal map, right?
Here,
calculation.
yes, definitely.
Yeah.
So and at least 2. So, okay, so suppose you have an Alford's Q-regular space. So remember, that means that an R ball has Q-dimensional Hausdorff measure comparable to R to the Q, right? And so here, although I haven't said it explicitly, that the measure I'll be using will be Q-dimensional Hausdorff measure. So then, if you look at the modulus of this pair, so again, you look at curves, you have a ball of radius r, a little r, right? And then that's the first set. And then you inflate the radius to some big R, and you look at the complement of that larger ball. Okay? So the associated curve family.
I can't see what the 2 sets are.
So the curve family will be the curves that start in the little r ball and leave the big R ball and go outward until they leave the bigger R ball. That's it's essentially, it's the radial curve family for metric annulus. And so the assertion is that this is bounded by this function here. So in particular, as the ratio big R to little r gets big, the denominator gets big and this gets small. Okay? So, and the proof, just take this, the most obvious kind of test function. You look at the distance function from the center of the ball, take 1 over that, and scale it appropriately till you get an admissible function, and then do straightforward estimates of mass. And you get this bound.
Yeah, I remember this definition is so complicated, you can actually use it to prove things. You just choose these test functions from the picture.
Yeah, it's
prove things.
I mean, the definition is worse than the proofs. So let's amplify this a little bit. Okay. So suppose you have a no. That just writing down this function rho, scaling it with appropriate C, you get something that's admissible. And the point is that the Alford's Q regularity gives you control on how much mass the space has in a given annular region. So you can sum this up and get an estimate. So amplifying this, so you take, suppose you have 2 sets E and F. To find the relative distance between E and F, it's a scale invariant version of the distance. So the numerator, you take the usual distance, so the minimum distance from E to F, but then you normalize that by dividing by the minimal diameter. Okay? So if you scale everything, change the distance function on the metric space by some factor, this quantity is unchanged. Okay? So an amplification of that previous lemma, well, this doesn't look a little complicated, but it's supposed to be simple. Again, you're in Alford's Q regular setting. You have 2 subsets E and F, say disjoint. Well, then the modulus for the pair E and F is bounded by, oops, there's a typo here. This phi should be this beta. It's bounded by some function of the relative distance. Okay? So that's a function. Well, it depends upon the Q and sort of the Q regularity constants. There is a constant in the definition of Q regular.
So the V above is the Hausdorff distance?
No, just the minimal distance. Yeah. So this should be a beta. So all this says is you're given 2 sets E and F. If they're far apart in this scale invariant sense, then the modulus is small. Okay? And the proof is similar. Essentially, well, maybe I'll just skip it. You use sort of the same ideas. You can cover you take the set with a smaller diameter and then cover it with a controlled number of balls whose size is phi is beta. Yeah, sorry about the typo there. Okay. So the upshot here is you have an analytic quantity, this modulus, right? And then you have this completely comprehensible quantity, the relative distance. And by some nice miracle, this simple quantity controls the modulus. Okay. Now, so the key definition here is the following, which just says, so if you have a Q-regular space, and I just pointed out that in general, the modulus is bounded above by some function of relative distance. And this next property, being Loevner, is when the opposite, the other kind of bound. Okay, so Q-regular space is Q-Loevner. Here, if Q is required to be bigger than 1, and you have some function alpha, so that if you have two subsets E and F, then their modulus is bounded below by some function of the relative distance. Okay, so in other words, if the relative distance isn't big, then the modulus can't be too small. Okay, but there's an important requirement here: is the sets have to be connected. Okay. So
alpha as it goes to 0.
The relative distance goes to 0. That will blow up. Oh, no, it doesn't matter. Here, the key is that it's positive. It's positive. So you could go further and say things about, how you can choose the asymptotics of this alpha. But it's enough for now just to say that there's some positive function here. Okay. Actually, maybe I need this to be monotone. Maybe I need this to be monotone, the way I've set this up. All right, let's say this alpha is monotone.
Did Loevner do something with this?
I'm sorry?
Did Loevner do something with this one?
He did, actually. So Loevner sort of realized that first of all, the classical modulus between subsets in Rn has this kind of control, that it's controllable by just a function of relative distance. And also realized that a lot of the classical theory of quasi-conformal homeomorphisms can be sort of erected just based on this fact. Okay. I'm sorry, say?
The notion of modulus was it available in Loevner's time?
I'm not the right person to be answering this question.
It's a historical question.
So I'll use this brief form. Just say it's Loevner if it's Q regular and Q Loevner for some Q. Okay. And so the realization. So this came out in this sort of this great paper of Heinonen-Koskela. Was that you can really if you have a space satisfying this Loevner property, then you can carry over a lot of the classical theory of quasi-conformal homeomorphisms. Okay. So before I say more about this, I'm sorry.
Can you prove absolute continuity of the all-force measure?
Yes. Yes. I'll get to that in just a second. I just want to give a few examples of these spaces. So Sm. With the usual metric. Now the sphere with this Carnot metric or sub-Romani metric that I was describing before, where the standard contact structure. And so as I said, when n is 2, this is the 3-sphere, and the metric has Hausdorff dimension 4. So it's actually all 4 regular, even though it's a metric on the 3-sphere. So a class of examples due to SEMS, if you have a topological n manifold with a metric, a distance function on it, which should induce the given topology, the manifold topology. If it's linearly locally contractible, this is the definition that I gave before, so no sort of bad fingers and tight necks, then, and it offers n regular, then it's a Löwner space. Okay, it's kind of an amazing, beautiful theorem. If you like manifolds satisfying Ricci curvature bounds, then non-collapsed Ricci limits are Löwner. The Fuchsian buildings, so I alluded to that briefly before. And then there's a class of examples. So the first one that I know of came from Loxo, but you can get many examples by taking limits of sequences of inverse systems of graphs. Again, I'm just not going to go into that for time reasons. So the Löwner condition easily implies some a couple of properties, though. The first one is quasi-convexity. So here, 2 points P and Q in a Löwner space can always be joined by a path whose length is comparable to the distance. Okay, so these are almost like geodesic metric spaces. Okay.
If you took the circle and unwrapping it, took the inverse limit, you get a solenoid. It's an inverse limit of graphs. It doesn't look like it has that property, though.
It definitely doesn't. I probably shouldn't even have put that up there. Yeah, pretend you didn't see that. Because actually, what I meant to say is you can produce many examples. You have to put some specific conditions on, and that certainly would not.
Trees growing out.
Yeah, I mean, it's...
Snowflake trees.
Maybe afterward I can describe them to you. So there's some very...
Well, certain inverse limits of graphs.
Yeah. So it was probably a mistake to put that there. Okay, quasi-convexity. And then... so that says, given 2 points, right, you can join them by path of controlled length. Now, the second condition here says, if you take 2 points lying outside an R-ball, then you can join them by a path outside some shrunken ball. So you take 2 points lying outside an R-ball, well, then you can shrink the radius by a controlled factor and join the points in the exterior of that smaller ball. Okay? So in particular, that tells you that Löwner spaces can't have what are called local cut points. Local cut point being a point that has a connected neighborhood that becomes disconnected upon removal of the point. Like in a circle has local cut. Every point is a local cut point because you can take an interval neighborhood and remove the point, and it separates. It becomes disconnected. So these Löwner spaces have this property. Now let me mention some. So when did I start? Is it 25 past? I think I started, it was 25 past, huh? Okay. So they showed that if you have a quasi-conformal homeomorphism between two Löwner spaces, then it's actually Quasimobius. So again, the quasi-conformal homeomorphism, quasi-conformal condition is this kind of infinitesimal condition where you take a limb soup of the eccentricity of ball images, right, at each point. And the Quasimobius condition is this macroscopic kind of global condition. And what they show is that the infinitesimal condition implies the global condition. And the proof uses modulus to kind of link the small scale, infinitesimal scale, with the global scale. Limb soup.
There was some big result of this kind just in the classical setting.
Yes.
Okay.
Isn't this problematic for diffeomorphisms of the circle?
Yes, everything requires that. That's where this Q big. We're requiring Q at least 1. I mean, strictly bigger than 1 to avoid precisely that. So again, so the first step in the proof is is to argue that if you take compact connected sets in the domain, you look at the image, you look at their images, then the relative distance between their images is controlled by the relative distance in the domain. Okay? And the way of doing this is to use modulus. So the idea is if you know the relative distance in the domain, then that gives you a lower bound on the modulus between those two, on that pair. Okay? On the other hand, if the images had large relative distance, okay, then the modulus in the target would be small. Okay, by the upper bound for modulus. And then using the quasi conformality, you can somehow pull back the admissible function from the target. Okay, so that's sort of a extremely vague sketch, but that's the spirit of the argument for getting this. All right.
So what are the hypotheses on the dimensions behind the cube?
Q is at least is strictly bigger than 1.
What if you take a circle and make a snowflake metric on it? Can't you still?
You can do that, but then it won't satisfy this Löwner property.
What?
It won't satisfy the Löwner condition that the modulus of the Q modulus of curves is possible. And then, well, the second step is to use this to see that the map is Quasimobius. So here, well, the idea is that this then tells you that if you have two, so the first step, you take two compact connected sets with controlled relative distance. The image has controlled relative distance. Now you want to get from that to the Quasimobius condition, which is a condition on 4 tuples of points. So the idea is, given a 4 tuple of points, you can promote that to a pair of continua by joining up the first pair of points by a compact connected set, say a path. And you can join the other 2 points by a compact connected set. And by using this sort of connectivity conditions I had on the previous slide, you can choose those compact connected sets so that this relative distance will be related to the metric cross ratio. Okay. All right. So other things that were proved here. So Jeremy Tyson showed that the Q modulus is actually a Quasimobius invariant or quasi-invariant among compact Q-regular spaces. So if you have 2 Alfor's Q-regular spaces and a Quasimobius homeomorphism, then the modulus of a curve family in the domain will be comparable to the modulus of the image curve family in the target, just as I said before in the case of, say, Romanian manifolds. Right? So a corollary of this is that the Löwner property is itself Quasimobius invariant, because it's a property which relates relative distance, which is easily seen to be Quasimobius quasi-invariant, with modulus, which is quasi-invariant by Tyson's theorem. Okay? Another fact that carried over, so there are different ways of completing this argument, so that's why I put up these other names. But if you have Q-Löwner spaces, so then every Quasimobius homeomorphism is absolutely continuous with respect to Q-dimensional Hausdorff measure. So you take a set with 0 Q-dimensional Hausdorff measure, you apply this QM homeomorphism to it, you get something with 0 Q-dimensional Hausdorff measure. Well, it doesn't have to be. So for the circle, it doesn't have to be absolutely continuous, right? The proof doesn't work. So, right. So in particular, in words, this is saying that this measure class, this Q-dimensional Hausdorff measure, is QM invariant. Okay. So another feature, this is another generalization of a classical fact. If you have Q-Löwner spaces, Quasimobius homeo, then it's a Sobolev mapping. Okay, so I don't want to define that, but it in particular means the following. You can find a Borel measurable function rho on the domain so that if you take a curve in the domain, take some curve gamma in the domain, you look at where the map F sends the endpoints of the curve. Okay? Well, then you can control the distance between those two image points by the line integral of this function rho. Okay? And this rho is Q integrable. All right? So in fact, this is a way of defining what it means to be a Sobolev function. Okay, W1Q. But so this generalizes this ACL property that one has for quasi-conformal homeomorphisms in the classical case. Okay, maybe I'll just state this one more result. So if you have a Livner space homeomorphic to the two-sphere, then in fact the Q is equal to 2 and it's Quasimobius homeomorphic to a two-sphere. Okay. Right, so now I think I'll stop before covering the last slide.
This kind of category kind of thing does not happen in dimension 2,
right? In particular, yeah.
And it's highly not true if you go like dimensionality 2.
Yeah, it's false. It's false. The analogous statement is false because of its examples. Yeah.
What is involved in the proof?
Okay, so the idea is so you're trying to produce this Quasimobius homeomorphism, so you're trying to produce a map. So the first question is, how do you get a map? Well, ultimately, you rely on the classical uniformization theorem. Okay? How can you use the classical uniformization theorem? Well, you start with this two-sphere. It has a metric on it, right? So you take some net of points, and then you use the Livner condition implies something like the linear local contractibility. It implies this linear connectedness. So if you take 2 points in the net, you can join them by a path. In fact, an arc whose diameter is comparable to the separation. So you take this net, and then you join all nearby points by these paths. And you get some network of curves. And you do a little bit of simplification, you get something which is topologically a finite graph with complexity bounds on the scale of the net. Then you subdivide and you get a triangulation. So now you see a topological triangulation of the two-sphere. So you can define a polyhedron, right, where you think of each triangle as an equilateral triangle of side length 1. Okay, so this is now a metric polyhedron, which has a conformal structure, which can be uniformized by Köbi. This gives you a map from that polyhedron to S2, and you can restrict it to the vertex set. So you get a map of the vertex set, which was a fine net, into the two-sphere. And so the key is, so this is sort of the beginning of the argument. The key is to get a uniform estimate to see that those maps, suitably normalized, are uniformly Quasimobius on the finite sets.
Any other comment, question? I think